That homework will be due this Sunday. Then I'm moving into chapter 27 today, which isn't on this homework, on color. It'll be due next Wednesday. Because, friendly reminder, our exam on this stuff, gee, it snuck up on us. I guess we have a week, but it'll be next Friday. Last normal exam, though. Yay. All right. And this weekend, I start reading all about your superpowers. That'll be good. Don't get excited. I know I won't finish this weekend. So, any questions about scheduling and whatnot? Yeah.
I have a question about the
Sure.
real paper. I turned it in online, but I was sick the past few weeks. So I remember that you turned in a hard copy.
Yeah, the instructions are the two. Get it to me as soon as you can then. Okay, anything else? We're more dense over here in this corner today. Okay, well, the last thing to discuss then with the chapter of light was shadows. Shadows, and then I'll review a little of it. This might work better with a little less light. Now, shadows shouldn't be too much new to you, right? Yeah. Get a bird. How many did puppet shadows when they were kids? I did. I still have a book on it. I was never great, but that was my favorite one, the bird. Anyway, with shadows, it's light waves, and they're trying to get around things. And we'll do more what's going on there. But here, you can just think of the rays. They travel in straight lines. We learned that waves can refract. Remember, change direction when they change mediums. These aren't changing mediums. So for now, we'll just picture a ray that goes straight from one point from the light source. But if an object gets in the way, obviously it blocks it. And so no light hits there, and you get a shadow. You're like, duh, I didn't need a physics class for that. There's a few names, though, and something that many people don't realize. Can you look closely? Especially if I get farther away. Oh, that's what my laser pointer's for. Let's look at my hand. So, that's better. Here it's nice and dark. And in the middle of my finger is nice and dark. But see how the edges are kind of blurry and fuzzier? They're not as dark, they're more gray. Okay, you can make that out. I didn't know if I was too close. Well, that's because it's not blocking all of the light, but some of the light. And these have names. We call this the penumbra. I'll write them on the board, but they're in your book. The penumbra. And the dark spot where it's completely blocked is the umbra. Umbra and penumbra. There's two types of shadows. Hey, where's Candelaria? This is her stuff. She loves photography and cameras and just did a project, and she had those terms in her presentation. She's going to be all over this. She's going to be sad. Anyway, let me draw that on the board so we can relate and show you a few more shadows, things that change with it. There's nice pictures in your book too, but if you had a light source, like the sun obviously, and an object, opaque, and a screen. So you just kind of work these out. Let's see. Light rays go off in all directions from the light source. Some go this way. They can hit the screen. That one hits the screen. These get blocked. And then it can hit the screen again and then out here. So right here, there's a shadow. From the rays on this side. I did draw that exactly how I wanted. Let's see, we can go a little further. Let's say there's one right here. That one, the extremes would be there. And from that side over to here. And it works from anywhere you come. So for there's a shadow from that light. Let's just skip to the other extreme, this side. You know, light, light, light. This one, you know, we can still get light in this region, but then it gets blocked till it gets to the other side. And these two make a shadow here in that region. So there's an overlap. Where those two extremes overlap, they come. Right in here, there's a dark shadow. No light hits there from anywhere from the light source. That's the umbra. What we usually think of as a shadow. But over here and over here, part of the light gets blocked, but not all of it. That's the penumbra. And up here, they have names to differentiate the shadow. Does that make sense? So, who watched the Lunar Eclipse last weekend? Yeah, that's why I liked you. That's it? One? Oh, it was fun. I took pictures. That is, you have the sun, and the Earth casts a shadow into space. It looks like this. And the moon, as it goes around in its orbit, becomes perfectly aligned. And based on the size of the moon, it goes through here. But it passes. You can think of the moon as kind of going around in its orbit like this. Not to scale. The astronomers in the department cringe. But so the moon comes around, and if it's perfectly in the same plane and aligned, that's when we get lunar eclipses. If it only passes through, because you know it can be coming like this too. It could be coming around this way and through it. But if we're in the same plane like this, it works out better. You're more likely to get total lunar eclipses. And the moon will enter this part. And most people never notice that. But the moon will get a little dimmer because it's in the penumbra. But they like it when it starts entering the umbra. And that's when you can actually notice that it starts getting eclipsed. You know, if you're looking at the moon. If we were doing, well, whatever. If this is just the bright spot and this is the dark, then that's the moon moving into the shadow of the Earth. And we notice it when it is going into the umbra more. And then it comes back out and brightens. But then when it exits here, it even gets brighter. It's just less of a noticeable effect there than it is there. So that's our lunar eclipses. Solar eclipse is a different order. That's when the moon gets in between us and the sun and blocks the sun. And there's actually a shadow of the moon projected onto the Earth. And if you live in that path where the umbra passes, you'll see, if it's a total eclipse, you'll see it in totality. If you live somewhere else, you'll just be in the penumbra, and you only see a partial eclipse. But it's just the shadows of the Earth or the moon on one or the other. Yeah?
So is the focus point of where like the outside edges are sharp is where those like two lines cross?
Right here?
Yeah.
I wouldn't think of it as a focal point. When we draw lenses that are curved or mirrors, they can bring light rays together, and where they converge and cross are considered focal points. Is where you're getting at. But this is shooting light out everywhere. It's not bringing all of its rays to a focus here. I just picked a few rays out, and they cross. You know, a ray here can cross there too, or a ray here can cross there. But they can also go this way and this way and this way and this way and this way. And so it's not really a focal point, but rays are crossing, crisscrossing all over the place. I just use that as the extremes to help demonstrate why we see a dark shadow and a semi-dark shadow. Now look at this. If we made the light source smaller, if it was more of a point source, and you had that object, you can play the same game. See, they still crisscross. But can you tell there's less of a difference for the penumbra? The shadow appears to be sharper because the penumbra section is smaller. And it's just because the light source is physically smaller. You could do a similar thing. You could make this look smaller if you took your object and moved it further away, couldn't you? If you got really far away, it would look like a smaller light source. And it would create crisper shadows. Let's see this. So we have, here, I'll pick this. There's a shadow. If I get closer to the screen, I'm farther away from the light source. That's more like a point light source. And can you tell the shadow gets sharper? The edges look crisper. If I get further away, the penumbra spreads out and you can see the fuzziness. Now let's switch to, it's just this. The light rays are trying to get around it. When you're closer to it, it can block more of them. And the penumbra can spread out from the two sides it gets to. So the closer you are to the source, or the object is, the bigger the light source looks. And it's spreading the light out more evenly. The farther away you get, it looks smaller and smaller. And approaching as if all the light came from one spot only. So it'll all get blocked more the same by the object. Did that help? Different object. There's a hole. This is kind of fun sometimes. Can you see how it's a little brighter right here around the hole? Can you guys make that out? Well, that's because some of the light is getting through one side to there, but being blocked by the other. So you can still kind of see the penumbra right around the edge there. And it's likewise around the edge of the whole thing. If I get closer, you can't see that as much. I can, but I'm probably blocking it for more of you. There, it's a little brighter there. Now let's change light sources. You guys all probably have one. Your smartphone's flashlight. Nice, bright, small light source, right? So let's look at it. Shine it on there. We can make it even darker. It's a lot sharper. Even if I get farther away, it gets even sharper. And even when I'm really close, that's a lot sharper than it was when it was close to the overhead projector. Again, because it's a small light source. Does that make sense? Out here you can't see it. My hand, see, now you don't even see that fuzzy region around my fingers. So that's how light rays go around objects and create shadows. Are we good with that? Now you can observe that more. There's another total eclipse in the fall. I just forgot what month it was. So mark your calendars. You can look it up if you want to see that one. Remind me, I'll show you pictures if you want to see them next time I set up my computer, probably Monday. Okay. All right, my all-time favorite thing, color with light. Do you remember, I guess I'll come back to that. White light, we've talked about that before. Here's some white light. Shine it over there. That's all the colors. Yeah, there you go. Ah! Prisms, probably played with them or looked at them. They refract the light. When the light goes through it, it's going from air into the glass. Remember, it gets absorbed by a particle, and then it re-emits. And so it slows it down as it goes through the glass, and it changes direction. So if I put it in here, instead of ending up over there, it refracts and bends over to here. But each color has a different wavelength, and thus a different frequency. Which one has the longer wavelengths? Do you remember? I've asked you before. I can hear people answering, I just can't hear what you're saying. A little louder. Think violet has the longer wavelengths? You lose. It's red. That's why we're reviewing. Red has the longer wavelengths, and thus, since they all have the same wave speed, the speed of light, If the wavelength is longer, bigger, wavelength is longer, the frequency is lower. It's not vibrating as quickly, longer waves. Purple, this end, has shorter waves, and they're vibrating more quickly. Since they have different wavelengths and frequencies, they get affected slightly differently when they go through the glass. Each frequency and wavelength gets refracted slightly differently. Who's getting refracted the most? It wants to go that way. We're sending it through glass and deflecting it over here. Who gets deflected more? Purple. It's further away, so it's refracted more. Shorter wavelengths, you can note that shorter wavelengths, higher frequencies get refracted more. Long wavelengths, less. And that's why we get this, it's called dispersion. Dispersion. You can take white light and break it up into its constituent colors. Because they're refracted at slightly different angles. And why are they refracted at slightly different angles? They get delayed different amounts going through here because of those frequencies and interactions with the glass particles. But every color's there. There's the rainbow. So let's mix colors. Let's go a little darker. I have 3 projectors here. I'll turn on. Here's a green light. Our eyes have cones and rods, the sensors that detect light in our eyes and behind our retina, the back of our eyeball. There's rods and cones. We don't, unfortunately, have as much time as I'd like to go into this, but rods are receptive to light and dark. They help us see in dim light. So we don't need much color. We don't see color very well in dim light because our rods are acting and they don't respond to these frequencies. Our cones, those receptors do respond to color. They work poorly in dim light, but they work great in bright light. And there's 3 main types: red, green, and blue. It's because the red one responds, it peaks. The biggest response is in the red part of the spectrum, my rainbow. And green, same for blue. There's some overlap, but they peak in the red, green, and blue. That's why the primary colors of light are red, green, and blue. The primary colors for pigments are something else. And we learn as a kid the primary colors to be red, yellow, and blue. Well, I'm here to teach you the physics why this is all so. The primary colors for light, red, green, and blue. Again, this is in your book. So let's mix light. If we take green light and we mix it with blue light, what do you think we'll get? Purple? It's this color called cyan. Yeah, this is what we're not used to. We'll do the pigments next, and it'll make more sense. So blue light shining here, it's reflecting off the white screen. This is white. You guys know that. Since it's reflecting off, it's white, it reflects everything off. None of the atoms or molecules or electrons are resonating with those frequencies. So it reflects them back. It makes them wiggle, and they spit it back out. So here, blue light comes to our eye, hits our blue cone, and our blue cone sends a signal to our brain and go, that's blue. Same with green. Well, here they're both hitting. Blue and green light are both coming to your eye. The blue's being activated, the green's being activated. They both send signals to your brain, and we learn and define that as a color called cyan. At least in English, it's called cyan. This color. So both of those frequencies of light are coming to your eye and activating your blue and green cones. Let's do blue and red. There's blue. You know what red looks like. What do you think you'll get? Magenta, it's called. This is called magenta. So there's red light reflecting off of here and blue light. Together, those mix in your eyes, and we call it magenta. Red and green is my favorite. What do you think? What? No idea? This was fun. Yellow. Red and green light mix to make yellow. So when you see something yellow, like this is yellow, that's yellow. That means this is reflecting red and green light back to your eye, activating the red cones and the green cones, and your brain says, ah, that's yellow. How about all three of them? All three mixed together. White, good. It better be, or my prism demo just messed up. There we go. See the center? Exactly. That's why I bought this. I almost forgot to wear it today. See? That's my... so there you go.
Why does this happen? Where do colors come from?
Where do colors come from? That's a good question. So there's electromagnetic waves out there. They have different frequencies. So we could say it's because of that. But some people say it's more physiological or subjective. We only see color because of those sensors in our eye. And the reason the primary colors of light are red, green, and blue is because of our physiology. But it's us. Other species, other animals, some don't see color. Some can see slightly into the infrared or in the ultraviolet. We can't. So it's because they have different wavelengths and frequencies, but everybody reacts a little differently. Was there a question?
Oh, it was more of a comment. It's not like saying, not like the question, if a tree falls in the forest,
It is similar to if a tree falls in a forest, does it make a sound?
don't the waves still exist?
The waves still exist, yes. They're still there. So what we call a red wave, whether we could see that it's red or tell it it's red, it's still a wave with that frequency and wavelength, whether we can tell it or not. Yeah. So the reason they're primary colors, just like with pigments, you can make any other color with just these three. These are the only three cones we have, and we can see more than just red, green, and blue. We can see magenta, we can see yellow, we can see cyan, we can see gray, we can see brown. These are all the same intensity. You can get other shades by decreasing the intensity, the brightness, the amplitude of one of these waves. Let's do one. If I decrease green, let's see what happens. Now, do you see the yellow turn to orange? Orange light is red and green light coming at us, but the green's not as bright. And that's how we see it. We call that orange. A little dark. Let's make both red and green darker, and it kind of looks brown, or it would. More brown. You can play similar games. Let's see. Let's try decreasing blue and see what happens. Look at the magenta. Maybe now, people have different terms for it, but it's more purple or more violet. Now maybe it's more fuchsia or magenta. You can have fun with this. Look at the middle. Let's put them all bright again. We got white in the middle. Let's make them all not as bright. Still looks like white in the middle, but it's not as bright. We're starting to get gray. You turn them all off, and of course you get black, because there's nothing there. But here's my all-time favorite thing, I got to admit. Let's get it white looking again. There-ish, that look okay? The shadows. First time I saw that, I thought that was totally awesome. Let's think it through. Let's come over here to the blue. That's blocking the blue light, so obviously we get a black spot. You can see the umbra there? It's black, because we're blocking blue from hitting there. Same with red. But what if we do it here? Can you see there's a red shadow and a blue shadow? So what's happening is, here we're blocking the blue light, and so only red gets there to reflect to our eye. And here we're blocking the red light, so only blue light reflects to our eye. You can do that with the yellow. That's blocking the green. That's blocking the red. All right, what two colors make up yellow? You're going to need to know this so you can start memorizing this. Yellow is red and green. So what color is being blocked? That's red light and green light, but not blue light. So sometimes I think of yellow as not blue. Cyan is blue and green light, so that's blocking the red. Magenta is red and blue, it's blocking the green. So you get these fun shadows. Wow. Hello. Look where I blocked it all. This is red only, so I'm blocking the green and the blue there. You can have all kinds of fun. Let's look at some colors. Oh, here's a red piece of fabric. You can tell it's red. Red light reflects off of you. But it's absorbing green and blue. It resonates with its dye and it absorbs that energy. They go in to increase its internal energy. Its temperature is warming up as it absorbs green and blue. But it reflects red. That's why it looks red. So if you only shine red light on it, it still looks red because it reflects red. But what's it do to blue? It absorbs it. So it looks dark. Now these cloths aren't exactly the primary color, so it's not perfectly black, but you can tell it looks darker, right? Even in the green, it looks darker. Let's pick another color.
How does dye work?
We'll get to dye. Yeah, that's after this light stuff. Let's do green. Looks green. Should look green and green. That's good. Blue, though, oh, it's dark again. Now yellow that's some green, right? So we ought to still be able to see it. Yeah, because there's green light in yellow light, so it reflects. But there's no green light in red light, so it absorbs. How about one more? Let's do yellow. That's what it looks like. Doesn't change in yellow. Yellow is red and green. So you can see the red here. You can see the green there. But over here in blue, it gets gray. It's dark. There's not much color there. It's kind of dark. Again, this isn't a perfect yellow. So this is how we combine light to get different colors. Red, green, and blue are the primary colors of light. We say cyan, magenta, and yellow are the secondary secondary colors for light. Yeah. The thing here, let me turn these off because I can't hear you. Go ahead.
Like the dress, some people say white and gold, but it's like a little black.
Oh, that illusion? Yeah. That gets fun. Oh, I'm going to need that. Briefly, is darker colors, it's that light, that interplay between the rods and the cones, and what colors we get more receptive to in what light we see it. You know, as I dimmed the lights, it looked gray, but you guys knew it was white. Your brains learned that. And if I had just asked you, what color is this? Most of you would have said white, even though it's darker than our first white. So lighting can affect things a lot. So can that interplay. Most illusions are we see one thing, but how that signal gets to our brain and is processed, this can be something else. And that's quite often how we get illusions. Let's put your minds at ease more and explain this color mixing with subtraction. This was adding light. We were adding light. Now we're going to subtract light. That's what pigments and dyes, your markers and crayons that you're used to, did. A lot of artists don't like this lecture because it confuses them. Still, you can go with red, yellow, and blue to help you paint. Okay, here's magenta. And I have yellow and cyan. All right. What's that? Go ahead. Yeah, aqua and cyan are very similar. Yeah, yeah. What this is doing is white light's trying to pass through it. It looks cyan. That means it's reflecting which two colors? Which two add together to make cyan? Green and blue, good. So this doesn't like the red. So if we put white light through it, it absorbs the red and it doesn't get through, just like it doesn't reflect off. But the blue and the green do get through and we can see it. So what we're seeing is light. They're adding in our eyeball, which is why it looks cyan. But what this pigment's doing is subtracting light. Just like this red piece of cloth, it's red because it's absorbing or subtracting out the blue and the green. Only red reflects to us. These transparencies are obviously transparent. So what color does magenta let through? Red and blue. So this one blocks which color? Green. What color does this one block? Red. Which one should get through both of them? Bluish. So again, this lets red and blue through. This lets green and blue through. The only one that gets through both is blue. These aren't perfect primary colors. I tried. But you get the idea here. Just like she noticed, that looks aqua. It could be slightly more aqua than cyan, you know. I tried. But that's what it is. This is blocking, lets red and blue through, so it blocks green. This one blocks red. Well, the only one that doesn't block is blue. So if you mixed cyan and a cyan crayon and a magenta crayon, they filter out and you're left with blue. So these are what we are technically the primary colors for pigments. For subtracting light, it's cyan, magenta, and yellow. But what we learn as kids is it's red, yellow, and blue. My personal theory is, because you don't ask little Timmy, you don't say red, yellow, I haven't done yet, and blue. Little Timmy, can you say cyan? Can you say magenta? I mean, they just look red, yellow, and blue. But technically, that's not right, and now you know. But you know, this one probably you could have guessed. If you take a red crayon, reddish crayon, and a bluish crayon, and you mix them together, you get purple, right? Well, that's what's going on. They're subtracting out different wavelengths of light and only letting that bluish purple one get through or bounce off. Blue and yellow, cyan and yellow, there's your green. See, this one lets red and green through. This one lets blue and green through. Which one gets through both? Green. Remember, yellow and blue make green. That's what we learned as kids, right? But technically, it's yellow and cyan make perfect green. You take a yellow crayon and a blue crayon, you don't get a perfect green, but it still looks green. All three, black, because no wavelength can get through all three. There's our red that gets through yellow and magenta. Is this making sense? This is laid out in your book, but this helps explain how all these wavelengths mix together and why various things in nature are certain colors, which is the rest of this chapter and lecture. So I encourage you to review this. Let's turn the lights back on. It might help you. We'll try something like this. It helps a lot of people I've shared it with. Or find your own method. So if you're adding light, if you add red and green and blue, you get what? You know this one, right? White. If you add red and green, what do you get? Green and blue and red and blue. Those are our cases, right? Red and green were, anybody remember? yellow, green and blue, cyan, red and blue, magenta. Kind of a way to think of that. Here's a trick one. What if you mixed yellow and blue? What color would you get? Yellow light and blue light. Add them together. Aqua, that's a good guess. Not right. What two colors are yellow? Red and green. White. Because this is red and green. Add blue, you're back to white. What are the other two? Let's see. If you mixed red and green made yellow, green and blue made cyan. So if you mix cyan with red, you'd also get white. Because this is green and blue. Red, green, and blue. And what's the other one? Magenta and green. Because magenta's red and blue and green. You get white. And again, you change the intensities, you get different shades. Oranges, browns, chartreuse, apricot freeze, whatever. All those Avon colors. For subtracting, we had cyan, magenta, and yellow. Also, if those are all pigments, they absorb everything and you get black. They subtract all light out. Because this one's subtracting blue and green, this one red and blue, that one. So you're getting the red, the blue, and the green in there. When we did these, we combined cyan with yellow. We combine cyan with magenta, and we combine magenta with yellow, and we'll see if you guys remember. Cyan and yellow both subtracting out, left what? See, I just think it through. This one lets what light through? Blue and green. Right, green and blue. Let's do that. That lets green and blue. What's this one let through? Red and green. Which one gets through both? Green. So these will subtract light out and only let the green come. So that's what we see. How about this one then? I heard one person say it, but they didn't sound confident. But you were right. Red or blue?
Red and blue.
Red and blue. This one lets green and blue through. This lets red and blue through. So the only one that gets through both. And you probably guessed then this one's this one. Red and blue, red and green. Red and blue, red and, so only red gets through because these subtract out the green and the blue. So let's do one more. What if you took white and you subtracted out red? What do you get? The rest, which is green and blue, which together make cyan. So that's how pigments and dyes work. They're just subtracting out light, and you see what's left. So you can think of cyan, magenta, and yellow as the primary colors for pigments, for subtracting, but they're the secondary colors for adding light. It's the combination of light that we see that tells us the colors of everything. Your red sweatshirt is absorbing blue and green. It resonates with it, they absorb, and the red light reflects back off to my eye. Your purplish shirt, that's kind of there's a red and a blue in there because it's kind of magenta-y. So I know your shirt's absorbing green because I'm not seeing much green come off of your shirt. That make sense? Is this at least starting to sink in? Okay, great. This piece of glass, what color is it? Can you tell? Enough light shining through it for you? Yeah, it's blue. Does that help? So, what's going on? Why does it look blue to us? It must be blocking out green and red because only blue light's getting to our eyes. So the dye in there is doing that. Good. So, those questions you probably asked your parents when you were a kid. First one I got on here is, why is the sky blue, Mommy? Who's ever asked that? Who's ever wondered? Have you wondered why the sky is blue?
I was actually going to ask that.
Well, all right. Well, I like working backwards with these. Now it's this adding and subtracting of light. And there's different ways to do it. It can be absorbed. It can also get scattered. If the light is subtracted out because it gets absorbed by a dye, but there can be particles in the air too that can scatter. You know, if light's coming at you, Patricia, and some of these frequencies get scattered that way, you won't see them. So it's like they're being subtracted out. The sky's blue. It's more like a cyan though, right? It depends on the day. But we'll go with blue. So what colors must be, what's going on is the sunlight. What color is the sun? Because that's the light that's causing us to see the sky. So let's start with a light source. What color is the sun? It is white. If you went out in space, it would look white. A lot of people say yellow. This will make sense. So let's start with white light. It comes in, hits our atmosphere. And what the atmosphere does is it scatters the blue light, blue side of the spectrum. And it scatters it everywhere. That's why the whole sky looks blue. It's like, white light comes in, hits a particle, and it scatters light in all directions. And so we see it as blue. So what wavelengths seem to get through the sky and pass straight through? Close, not the shorter ones, because blue was on the shorter end. The other end, yeah, the reds and the yellows and the oranges get through more. But that's why it scatters. The intensity of light that gets scattered is proportional to the wavelength. The shorter the wavelength, the more it gets scattered. Remember, the purples and the blue end of the spectrum are shorter, so they get scattered more. And it's to a fourth power. That one's not critical, but realize it's not a direct relationship, it's big. Remember how if you doubled the speed of something, you quadrupled the kinetic energy? Well, this one, the wavelength is to the fourth power, so it's a big effect. The shorter wavelengths get scattered a lot more than the longer wavelengths. So the blues and purples get scattered more than the reds and the oranges. Which is one reason, if you take the white light and you scatter the blue out, what's left? Red and green, right? So if you're looking directly at the sun, which you're not supposed to, what color does it look to us here on Earth? Yellow. That's red and green light. Because the blue has gotten scattered out, and that makes our sky look blue. But the light from the sun itself, the reds and the green make it through, and it looks yellow. You with me? Then what happens at a sunset? The sun gets lower and lower in the sky from our perspective. And when it's really low, it has to pass through a whole lot more atmosphere, doesn't it? Along the surface, where it's more dense. There's more particles. So more blue gets scattered. Maybe even some green gets scattered. Because there's more of it now. What's left? If you scatter the blue and you start scattering green, red. That's why sunsets look red. Because those longer wavelengths make it through, but the shorter ones are getting scattered. I think that's cool. So next time you're enjoying a sunset, yeah. Yeah, if our eyes were more responsive to violet, if there was more violet or purple in sunlight, and we were more responsive to it, even the ultraviolet, then the sky would look that color to us, because it would be scattered more than the blue. It is scattered more than the blue. It's just our eyes actually aren't as receptive to purple, and there's less purple in sunlight than there is yellow and green. So, a couple factors there, but yeah, good.
So if you didn't have an atmosphere and your magnet had to scatter
see white.
So the sun's up here, but
Yeah, so
we're looking over here.
Yeah, you're looking over to the side, but there's no atmosphere to scatter any light. So
Yeah, if there's no atmosphere to scatter the light, we wouldn't see blue over there.
yeah, what would we see? Would there be so much?
If there's nothing there, there's nothing to scatter the light or redirect it into our eye. No particles. So I would expect to see dark, black. If there was the moon, if you're on the moon, about all you see are light sources. They can see the sun if you're standing on the surface of the moon. You can see the earth. That's the sunlight reflecting off of the earth. But in between those out there, it's dark. Because there's nothing to reflect that light or scatter it back to our eyes. We only see light that goes into our eyes.
So why would the moon not be yellow either?
Why would the moon not be yellow? The sun reflects off the moon, and then that light comes in through the atmosphere, and it is actually slightly yellower to us here than it is if we saw it out in space. I've never thought of that. See, good thinking man's question. Why isn't it more yellow? I have to think about that. Because the blue in that light is being scattered, but it doesn't seem to be as much, does it? Yeah, I don't have a good answer for that right now. Good. Yeah?
What makes
A blood moon. Glad you asked. That's the picture I wanted to show you from the eclipse. So when it comes in here, when the moon gets right here, we shouldn't be able to see the moon at all because it gets blocked. But something cool happens once the really bright spot goes away and we're completely in the umbra, a total lunar eclipse. Something cool happens. It turns this orangish red. That's because the light from the sun that comes around the edges here gets refracted. It gets bent. I drew straight ones. But there's a little thin atmosphere here. And it's going from nothing into air. So it slows down, it's delayed, and it changes direction. And what happens is this light, let's say this one, it's coming, and instead of going straight, it gets bent slightly. And same on this side, bent slightly. And all this light is what's shining on the moon. It's not as bright, but what happens to this light? It just passed through all that atmosphere. It's like getting everybody's sunsets all at once. All that blue and a lot of the green light scattered out as it does that, leaving only the long wavelengths or the longer wavelengths to hit the moon, reflect off and come back into our eye. So yeah, it looks redder and oranger. Due to lack of time here, here's a slag rock. It's just got some suspended particles in there. What color does it look? Yeah, it's kind of opaque. It's not completely transparent. And you're seeing blues and yellows in there. A lot of the blue, let's see if I shine this, can you see the blue light gets scattered off? This is kind of like our atmosphere scattering the blue light to the sides. But check the sun trying to get through. What color does the flashlight look to you? More yellow, more orange. That's because the blue light's getting scattered out. You subtract blue from white and you're left with yellowish. That's what's going on. If you go through more of this, more will get scattered and this will turn red. One last one to think about, and I'll stop. Here's some wax. You shine light on it. It's white. When you see things that are white, what's it doing? Last question. Things that are white look white because they must be reflecting all wavelengths to you. So this is scattering wavelengths, but they scatter all of them. Clouds, water droplets, but they're different sizes. They're scattering all the wavelengths back to our eye. That's why clouds look white. So next time you see colors, you can just use this reasoning to figure out what's being subtracted out, what's going on. Groovy. Well, you guys have a great weekend.